Good morning, everyone. My name is Samantha Johnson from Team Earthnado. My teammates are Maggie Peterson, Ben Passolt, and our project manager, Jacob Stewart. Today, we will be presenting to you our design for the lateral force resisting system of Michigan Tech's new on-campus edition, the HSTEM building. But before I get into all of that, let me first introduce you to our scope of work and a little bit about the HSTEM building itself. The actual structure will be steel-framed construction with composite slab on metal deck floors. However, for the purpose of this senior design project, we decided to explore an all-mass timber alternative. Due to this, we will be using cross-laminated timber, or CLT in short, to make up our lateral force resisting system. For those of you who need a refresher, let me quickly explain what CLT is. It is basically a solid wood panel made up of layering boards in alternating directions on top of one another and bonding them together with structural adhesive, as you can see in the image. It is lightweight and its strength is comparable to that of steel or concrete. It is also more sustainable as it produces less CO2 emissions than other structural materials and can be made from recycled timber. So let's get into our design and what our role specifically was on this project. So we just heard from Team Gravs, who worked with the gravity loads. Well, we are the other structural engineering team, and we're primarily concerned with the lateral loads on the structure, namely wind and seismic loads. We determined which of these loads controls and how much lateral force each story of the structure needs to withstand. From these forces, we were able to determine how much linear feet of shear wall is required to resist these torsional forces. After this, we also had to determine the optimal locations for these shear walls, based on both aesthetics and engineering principles. After this step, and because we assumed our concrete floors to be rigid, we had to conduct a rigid diaphragm analysis, which we will get into later in this presentation. We also selected which hardware would be best for the job. Since we worked with the lateral loads, we also had to look at the connection between the ChemSci and HSTEM building. Even though the two are connected, in terms of lateral loads, they will act structurally independently of one another. However, we still had to size the gap between the two structures to ensure that when they sway laterally under these loads, they do not collide into one another and cause damage. Lastly, we also worked a bit with the micropile foundation and designed hard tension rods to connect the shear walls to the micropiles. So let's look at an overview of this presentation. I've already kicked us off with the introduction. Next, Maggie and Jacob will look at the wind and seismic loads, followed by Ben, who will delve into the shear wall design and rigid diaphragm analysis. We will then look at our connections and hardware, followed by foundations, before ending off with our conclusions and recommendations for the project going forward.
So first, we had to look at the wind loadings to decide whether wind or seismic loads controlled for the building. And we did this using ASCE 716, using the main wind force resisting system. And so we had to find the wind loads at each of the different stories, the first, the second, and the third. And we then calculated the story forces at each level using these wind loads. And doing this, we had to find all these different factors using different things from the building, such as the size, the location, the surroundings, and what the building's being used for. And then we also had to consider the ATC hazards. So first we had to find the ATC hazards using the risk category and the location. And we found a wind velocity of about 104 miles per hour. And so these are the wind loads we found for the north-south direction, which will have both wind directions for, unlike the east-south or the east-west, which will only have one direction because the ChemSci is blocking the west wind. And these are the east-west directions, and these are a little bit bigger because of the ChemSci building.
So as Maggie said, we had to determine loads for both seismic and wind. And unlike the wind load, seismic load is only focused on dead load, and it doesn't matter what orientation we look at for the building, just because it's just the dead load of the building. So included in the dead load, we had the member self-weight of all the materials. We also had, as mentioned in the Grabs team's presentation, the lab spaces have 6-inch concrete slabs to help control deflections, whereas the remainder of the floor space will be covered with 3 inches of concrete, which that concrete rapidly made it apparent that this building was going to be a heavy building for its size. We also had to include any partition walls and snow loads that would be on the roof of the building. So from using the ATC website again for our seismic loads, we found that we were a risk category 2. And we were actually in the default soil classification. All that is determined based on the fact that we are not in a very seismically active area. So therefore, we just have to meet the minimum seismic requirements for this region. And then from this table here, we only had to use these SDS and this SD1 value. Both of those values are used in our calculations to actually determine what the loads were per floor. And then these plots over here just represent the maximum acceleration that would be experienced by a building in the event of a seismic event, which up in copper country should not be a problem, but you never know. So what we found was that the roof load, with having a green roof and all the other dead load components, we had a 50.7 kip load. Now, it should be noted, this is with the green roof, a full green roof across the entire roof. If a partial green roof or no green roof is included, then that load is reduced, which still helps us out. And especially when looking at lateral movement, the load has to be transferred from one floor to the next. So what you'll find is that as we progress closer and closer and closer to the ground floor, the load increases, and that's simply because we're adding up the loads from the previous floor, from the floors above. So that's why the third floor will have a shear of about 69.8 kips, or 69,800 pounds. And then the second floor would have almost 80,000 pounds worth of shear load that needs to be moved to the ground floor. So in this diagram, we just have showing the exact breakdown. So we can see that the second floor has 9.5 kips of load of shear. The third floor has 19.1 kips. And then, as I said, for the roof, we have 50.7 kips there, for a grand total of about 79.3 kips to be applied to the ground floor. And so all this load has to be transferred to the foundation system below.
So just to touch on it again, this is a mass timber building, and mass timber buildings as a whole are relatively new in this part of the world. They've been in Europe for the past couple decades, and there's a few of them in the US, but overall in places, especially that are seismically active, they require like a steel moment frame, or basically just not a timber system to resist the lateral forces. And as of like a couple months ago, they've just installed this provisions to allow you to make an entirely mass timber building in the code. So we were kind of doing new stuff for our design. We were primarily using a paper written by Dr. Vandeland in 2020 about how to do this. He listed a handful of criteria that had to be met in order to design shear walls using CLT panels. And the criteria are platform framing. So this means the walls need to be built, and then the floors need to be built directly on top of the walls. You can't have the floors tying into the side of the walls. The panels need to be a certain size, certain ratio, so they're basically taller than they are wide. You need angle brackets, kind of shown in that image in the bottom right, to connect it to the ground. And then you need tension rods at the end to resist the wall from overturning. And all these provisions are essentially trying to create walls that will rock as opposed to slide. It's for multiple reasons, but the overall intent is they want the angle brackets, the steel angle brackets to yield before the actual CLT panel. It's safer, it's a slower yielding, it's, you know, gives you some warning as opposed to a brittle rupture of the wood. But yeah, these are all the criteria we had to meet. So we took that information and began placing the walls. In order to place our walls, we needed to make sure that we could have them go throughout the height of the building. In the previous presentation, you saw how like the second floor had a big gap in the middle of it. So obviously you can't, we don't want a wall just sticking up in the middle of the open space. So we had to see where it went all the way through the building. We had to make sure the gap between columns was large enough so we could actually fit our walls. And then I'll get into it in the next slide, but the location of the wall dictated its strength. So you couldn't have walls that were basically just one after another. They needed to have some distance between them because that creates a moment arm, which helps resist torsional stresses. So when we started placing our walls, we first looked at direct shears. Direct shears are basically just when you push on the building, kind of what resists it, kind of like a brace, I guess. So it's shown by these green arrows. So we first put those in, make sure it could resist the direct shears. That kind of gave us an initial starting point. But because this building, it has sensitive lab equipment, there was a concrete slab installed on each floor. That concrete slab we assumed to be rigid, which meant that the floor itself would act as a diaphragm, and if you applied a load to it, it would apply a load basically everywhere. So we had to perform a rigid diaphragm analysis. That basically accounted for the direct shears and also torsional shears, which were created by that concrete panel twisting. When you apply a load to it, it then twists, and that adds load onto other walls basically. So we took our rigid diaphragm analysis that we made and just tried multiple wall locations just to ensure that our location was ideal for not disrupting anything and still being strong enough, basically. So the rigid diaphragm analysis also gave us the total the stress applied to each wall. So we took that information to actually decide what panel we needed and what size we need. The size also, we need to account for that the panel ratio from the beginning, from the paper that we were going off of. So we ended up making all of our walls 11 foot. It's also just for simplicity, just so we can have a standard size throughout the building. We'd use the SLV3 5 alt layup panel. This would come from the Smartland, Alabama plant, so we need to get shipments from there. And assuming we use all those pieces, it should be strong enough to resist our loads.
So as Ben mentioned earlier, according to Vandeland's paper, we have to have platform construction. And to do that, we're going to be using ABR 225 brackets. These brackets, we can use them to bolt them to the ground foundations, but then for the second and third floors and to the roof, we'll also need to construct them in this manner, where there's the wall from the previous floor. We'll have the CLT panels that were developed through the Graves team, and there'll be angle brackets connecting. Now, these boxes here represent the concrete slab. And so the way this construction of this aspect of the building would go is that the floors would be placed, the CLT panels would be placed, and then the concrete topping layer would be placed on top of that, so which would effectively end up bearing these connections here. Now, we'd have these brackets evenly spaced throughout the entire wall, and it would encompass both sides of the wall in order to transfer the shear load. Now, as Ben also mentioned, there are tension rods, and these tension rods are to prevent or are to take up any loads that are resulting from the walls actually rocking. So these tension rods will be tied all the way down into the foundations, and they'll run along the entire length of the wall. We found that we could use an ATS SR 10H150 tension rod, where each wall would require 4 tension rods, 2 on each end, just to make sure that we are transferring this load. Now, as was also mentioned, these buildings will act structurally independently of each other. And to prevent racking, which is the actual impact of the two buildings on each other, we needed to include a gap, which we'll just call it a structural gap, where of 8 inches, which will then allow for these buildings to have plenty of room to deflect as they handle and take up the load as a result of wind, or if seismic occurs, seismic as well. That gap was mostly based on the deflection of chem-sci, with also the deflections of the HSTEM building. Now, because of when chem-sci was built, we're gonna assume that it's a little bit more rigid, because it definitely is more of a engineered structure in terms of it's got more concrete and steel to help out with its loads. But that also helps us out because with it being more rigid due to its weight, the gap can be smaller than before. And then in terms of our foundations, as the Gravs team mentioned, there will be micropiles, or at least we focused on the micropiles. So we're gonna have 4 micropiles at each end of the shear wall with a shear cap to help tie those together. And then we'll have concrete beams that run along between the shear caps and connecting to the rest of the Gravs team's foundations. So that way these foundations work in conjunction with their foundations to actually transfer all the loads down to the ground.
Okay, so in order to end off our presentation, I will quickly reiterate some of the most important points from our design. In order to withstand the lateral forces, the HSTEM building needs a total of 4 shear walls. They need to be 11 feet long and made up of smart lamps SL V3 5-ohm panels. The shear walls also need a total of 216 angle brackets on all edges, and we strongly recommend using Simpson's ABR 225 angle brackets for this. Each end of the shear wall also requires 4 tension rods to connect it to the micropile foundation. Lastly, ensure that the structural gap between the chem-sci and HSTEM building is at least 8 inches to prevent any racking from occurring. We would like to thank Dr. Dowden for being our advisor on this project. Special acknowledgements also go out to Jacob Gutter, our client, and Dave Johnson, our CLT expert at SmartLamp. Thank you for your attention, and we wish you all a very pleasant rest of your day.
Much. Are there any questions for anybody? I guess I have one question. I wasn't clear in your presentation. So you calculated wind loads and seismic loads. Did you say which one governed your design?
Seismic
Yeah, we
load.
didn't, but seismic did, yeah.
Okay, seismic. And that was just because of all the concrete that's included on each floor, which made this building very heavy in terms of a dead load perspective. So.
Okay, that makes sense. Yeah, we were a little surprised that seismic controlled is such a low seismic area, but okay. So interesting note. The paper that this team mentioned, Professor Vandelit, he started his career here at Tech. So he's actually used to be a faculty member here, but he's now at Colorado State. He was the one that led the effort in codifying CLTs, seismic force resisting systems. So, well, I think you guys, there aren't any questions. I think we can go to the next presentation. And so thank you again. Just want to check. Oh, we do have some people online.